Today I would like to talk about gravity and inertia. I say gravity and inertia because I agree with Einstein's thought that gravity and inertia are the same. Physicists use both Newton's formula and Einstein's theory of relativity to explain the force of gravity. Unfortunately, relativity does not reconcile well with quantum physics. We are told to use Newton's simpler formula for gravitational attraction when it fits, and Einstein's formulas when we need to. Neither formula works across the cosmic scales or explains inertia adequately. I propose that the origins of the problems for gravity can be traced to the Michelson-Morley experiment in the late 1880s. Looking for luminiferous ether to be the medium to carry light across the sky, Albert Michelson and Edward Morley built the first interferometer to measure the ether as it moved across the Earth. They did this by splitting light into two beams at 90-degree angles, then recombining them back together to measure any shift or change in velocity between the two beams. The thought was that since the Earth was moving through space around the Sun, there should be a detectable wind blowing across the Earth that was the medium for light. They reasoned if they pointed one beam from the interferometer in the direction of travel and one perpendicular to the direction of travel, there should be a velocity difference between the two beams of light. This was a brilliant experiment, but they were not able to measure the ether. Their experiment is considered one of the great failed physics experiments, because it failed to measure any shift between the two beams. Albert Einstein came along shortly after this had become accepted fact and was intrigued by gravity and made his theory of relativity and formulas based on this information. End of story. Today, I propose we do a thought experiment. Let's forget Michelson, Morley and Einstein for a brief moment. Let's clear our minds of preconceived notions of gravity and inertia. The questions are these. What if gravity followed classical physics rules? Are gravity and inertia equivalent? What would that look like? We are going to talk about inertia before we talk about gravity. Inertia is the basis, the simplest building block to understand the foundations of gravity. Once you understand inertia, it is much easier to understand gravity. I fully agree with Einstein's insight that inertia and gravity are the same. Maybe we can show why that is true. Let's set up the experiment. We are going to start with just empty space and add only negatively charged particles. Nothing else is required until we add mass. Think of this as deep space where nothing resides. You can think of this as a sea of negatively charged particles, or more appropriately, a negatively charged field without polarization or direction. Since we are dealing with deep space and planetary-sized objects, think big. The field charge distribution is even. Something to note about the field. The individual charges are all the same value. In order to change the overall field charge, we need to get them closer to increase the field strength, or further apart to decrease the field strength. Next, we are going to add a single mass. This will be planetary in size. Let us work with things we can all know about. This will be Earth-sized. Let us give it a mass of 6 x 10^24 kilograms. We will give it a radius of 6,387 kilometers at the equator. This planet has a gravitational attraction of 9.8 meters second at the surface. All the parameters we are familiar with. We will even give it a starting velocity of 107,000 kilometers per hour non-accelerating. A planet at rest, non-accelerating with a mass and size closely resembling Earth, The actual values are not important, but I wanted to use something people are familiar with. We are mainly expressing concepts here. We are asking the why. In physics, we are used to calculating single charges moving through a field, either electric or magnetic. In the case of gravity and inertia, those roles are reversed. In the case of inertia, or gravity, we have a field moving through a sea of charged particles, or a much larger field. If the smaller gravitational field around the mass is balanced, there are no net forces acting on it. All the forces cancel out and the net forces are zero, regardless of the values of the gravitational field or the surrounding charged particles. If it is moving at less than about 1/2 the speed of light, there are no other forces acting on it, hence it will continue to move in the same direction with the same velocity. These are principles we all agree on. Let's characterize the gravitational field of the planetary mass. It behaves like a monopole field. It has a center, or pole, with field lines, like magnetic lines, radiating outward. The gravitational center is the north pole of the gravitational field. This is where everything is attracted to. These field lines are semi-rigid like magnetic field lines. They can be bent, as they are when the planet or mass rotates at high velocity. Think frame grabbing if you like. These field lines are firmly attached to the mass. If the mass moves, the charge moves. If the charge moves, the mass moves. This field also has a perimeter where its effect stops or ends. Beyond that, there is no attraction to other masses or objects. The mass has the opposite charge as the space around the mass. We'll call the charge for the mass plus g and the charge for space g to keep them separate. They do behave as opposites. When you think of these charges, you need to think weak. The individual charges are so weak that a small mass like the Sun or the Earth does not repel the g charge from its proximity. There is plenty of g charge at the surface of the Earth and all the way through. As the plus g field gets stronger, the g field gets weaker, or has less effect. Now that the parameters for the experiment are explained, let's see what inertia is. We are going to accelerate the planet by pushing on the mass towards the right. We will use Newton's F equals ma law, or Euler's to be technically correct, as a basis for understanding. We know that if the acceleration is zero, the force is zero. We know that when we push the object, there is a force pushing back. And we also know that as we move faster and faster, it takes more force to keep the same acceleration. What could be happening to do this? It appears that when we move the planet or apply force to the mass, the field gets distorted. It gets distorted in a peculiar way. It becomes egg-shaped. The field lines on the right-hand side get closer together, and the field lines on the left-hand side get further apart. There is also more field lines overall on the right-hand side versus the left-hand side, when we look at the perimeter of the field. Now the overall volume of the gravitational field does not change, but the result is that the field becomes unbalanced. The gravitational center moves towards the force, away from the geometric center of the mass. The field lines are held in the same place on the perimeter of the object. This unbalance causes more force to be applied to the right-hand side of the gravitational field than the left-hand side. This unbalance of the plus g gravitational field inside the g charge is the force that is pushing back against the acceleration. The more force we apply, the more the plus g gravitational field gets distorted and the more g force that is pushing back to resist the acceleration. If we stop accelerating the object, the gravitational field returns to a balanced condition and the velocity stays constant. Again, with no net forces acting upon it. If we accelerate the mass, the distorted field, which is attached to the mass, pushes back. If we accelerate the mass at a constant 1 meter per second acceleration, we will get a force directly equal to the mass pushing back against us. Also, as the velocity increases, it takes more force to keep the 1 meter per second acceleration. This is because the gravitational created in the mass field is increasing. If we agree that Higgs field is the field that imparts mass, it is most likely imparting a gravitational charge directly proportional to the velocity. There are two conclusions we should come away with if we examine inertia in this manner. First, gravitational field is directly proportional to matter and velocity. Mass is equal to gravitational field, not the sum of matter. Matter has a small intrinsic mass, but the predominant mass is the plus g gravitational field. The faster the matter moves through the field, the larger the charge that is created. This is a linear progression. We also know that as we get close to about 1/2 the speed of light, there is an additional force acting upon the mass to resist acceleration. This additional resistance is the g field itself. In an oversimplified explanation, above about 1/2 the speed of light, the g charges do not have time to move out of the way of the plus g gravitational field. As the mass moves faster and faster, more g charge builds up to resist the acceleration. If we remove the accelerating force at this point, the object will slow down until this force is eliminated, and only then it can come to a constant velocity. We talked about inertia and gave a reasonable explanation of the mechanics. So, how do we explain gravity? How is gravity like inertia? First, let's look at Newton's formula for gravitational attraction. We are also showing Coulomb's law for electrostatic forces and acknowledging the similarities between the two inverse square laws written almost 100 years apart. Please remember that Newton first published his work in 1687. Coulomb published in 1785. It was remarkable that Newton was able to formulate these simple laws, not having the framework of electricity. We'll start the experiment this time by adding a single planet. We will omit the g-charged field for the sake of simplicity. This is the same object we had with the example for inertia. We have the planet and the gravitational field around it. Next, we will add the Sun to the experiment, or put the Earth in orbit around the Sun. Nothing else has changed. The question is, how does the Earth get attracted to the Sun? The answer is, the gravitational field around the Earth looks just like the experiment we did with inertia. In this case, there is no force pushing the Earth from the left-hand side. Now in this case, the gravitational center of the Earth is attracted to the gravitational center of the Sun, producing the same effect. This is like magnetic poles attracting each other. First, the gravitational center of the Earth is moved towards the Sun, then the gravitational field of the Earth is distorted to the shape on an egg, and then the g-charged field that both objects are in moves the Earth towards the Sun, and the Sun towards the Earth. This distortion in the gravitational field is important when we think about why orbits are ellipses and not circles. This distortion of the gravitational field around the planet forces orbits to be ellipses due to the varying gravitational effects around the planet. The side with the longer gravitational field has a stronger gravitational field at the same distance from the planet's surface. This is not very pronounced close to the surface, but as the distance increases, the effect gets larger. This is why inertia and gravity are identical. They both change the shape of the gravitational field around an object. The unbalance in the gravitational field causes the mass to move inside the larger g field. So, we have demonstrated a reasonable hypothesis that mass equals gravitational field charge. There is only one mass. So m1 equals gravitational field 1 and m2 equals gravitational field 2, or charge in Coulomb's law. So, what does g equal? This is the negative gravitational field charge in space. Scientists have been trying to measure this with some precision for quite some time. This is called the gravitational constant. Now, scientists have been trying to get a precise measurement of the gravitational constant for a while now. They have been trying to precisely measure this since the days of Cavendish in 1798. If we follow the logic where the gravitational center of the Earth is shifted to one side, always towards the Sun, as theorized earlier, it may be difficult to accurately measure the gravitational constant with any certainty. As the Earth rotates, the distance between any fixed measurement point and the center of the Earth is always changing. Also, as the Earth rotates around the Sun, the distance is changing as well. Since the Earth is tilted, in the daytime the measurement is closer to the gravitational center than in the nighttime. Also, it is always accelerating either up or down depending on the time of day or evening. And the difference between summer and winter time measurements could be significant, because the gravitational center would be in the opposite side. The Moon's orbit around the Earth will also add some variation. Looking at the problem this way, one thing we could do if we wanted to solve the measurement problem is to add more measurement locations and synchronize the measurements so that they could be analyzed together, and positional and acceleration errors could be averaged out. At least 2 measurement stations on the northern hemisphere and 2 in the southern hemisphere would be the minimum. I would strive to keep these on the same latitudes above 25 degrees north and south to eliminate directional changes in the measurements and keep in pairs on the same longitudes. Doubling this to 8 total measurement points would be my preference. There is some talk that the gravitational center is behind the line between the Sun and the Earth by the time it takes for light to reach the Earth from the Sun, about 8.3 minutes. This hypothesis predicts that the gravitational center of the Earth is always pointing directly to the Sun, or more precisely pointing to the axis of motion. The reason for this is it lines up to the gravitational field lines from the Sun, like a compass. If the gravitational center of the Earth was pointing 8.3 minutes behind the actual straight line to the Sun, we would be slowing down measurably. This should be able to be measured and verified. I mentioned earlier that I thought the first wrong turn with gravity was the analysis of the Michelson-Morley experiment, first performed in 1887. They were expecting to measure the luminiferous ether moving across the surface of the Earth. I would expect this to be impossible. Of course there are g charges at the surface of the Earth, but the rigid plus g field lines inhibit the free flow of the g charges within the plus g gravitational field. Think of a densely treed forest. There could be mild winds on the tops of the trees, but at ground level, you would hardly be able to tell. The air is still there, just not moving in any particular direction. When we say about gravity that every object in the universe attracts every other object with a force which is directly proportional to the product of their masses and inversely proportional to the square of the distance between them, there is a caveat. Those two objects must be within the same gravitational field. If they are not, there is no attraction. I am skeptical about the idea of a gravitational constant. G. Newton's formula works well for all cases if we accept this premise. If we allow for G gravitational value, rather than gravitational constant, current formulas work without relativity. Nearing black holes, for example, there may be very little G. The Earth's gravitational center always points towards the Sun. Gravity and inertia are the same effect in that the distortion in the gravitational field produces the force to move the object. Gravity is the field moving the mass, inertia is the mass moving the field. Mass equals the gravitational charge always. Matter is the skeleton to which the gravitational field is attached to, and the two cannot be separated. Mass increases when velocity increases. The Michelson-Morley experiment not the correct way to measure luminiferous ether. If you made it this far, I would like to thank you for watching. I tried to simplify this as much as I could to make it easy for people to understand and to criticize if I am wrong. If you have questions or comments, please leave them. If more than 20 people like and agree with this, I'll make another video about the photon and what makes up a photon and how it moves, why gravity bends light, why light has mass, and why gravity and light move at the same velocity. Also, if there are any Blender programmers out there that can do good planetary simulations, please reach out to me. Maybe we can make a deal. I would love to get off PowerPoint graphics and make something that really shows the visualizations. Take care and thanks again.